now. So how do you want to structure this? Since it's just the two of you, we could either work on some specific questions that you do have, or we basically would just walk through it one by one, like line by line through the lab. Did you have any specific questions, any specific problems that we want to discuss?
Would it be okay to walk through this one line by line? I think if at the end I still don't understand something, I will ask a specific question.
Okay, sounds good.
Thank you.
So, no, of course. Abigail, you're always on board with this. Let's do that first, and then let's go into the specifics. Okay, good. Okay, so I have posted now the answer key that should have gone online at 6. So that should be available now. So now the submissions are closed. All right, so let's go to the beginnings. So this is basically just a knitted starter. And then we have, so most of this was given already, right? So this is essentially the assignment. So we have the assignment now. So we're doing essentially the same things as we did in the lab, we're just doing them for different parameters and different data set. So the idea was that we have an enhance, or let me share my screen, I'm not sharing the screen. Getting confused. Okay, good. Okay, so we're looking at data from the enhance in SPSS format. We know how to load this, we've done that. Fit a multiple variable model that has the response variable of blood pressure. And we're looking at education as a study variable and male as confounders. So first step essentially is to just run same coding that we had in the, so I'm going to run it in the console, so I'm not going to do the markdown. So this is the knitter, echo equals true. That's essentially, so what echo does in essence is you can also add it to each of the chunks. So these in markdown, these are called chunks. You can add this command also to each respective chunk. So I have not programmed this RMD code. So this is Marcel Ambino who did that, or maybe Professor Zhang, I'm not sure. So they choose to kind of generally, globally kind of set this all to echo equals true. So echo equals true means that it will show the respective code of each chunk. If you do echo equals false, it will not show the code, it will only show the output. You can do also include equals false, which will then not show anything at all, but will only show plots and actual results. Then we have library Haven. This is one of the ways how to load SPSS files with the read underline SPSS function. There are others. There's, for example, the foreign package also allows for you to load SPSS files. Usually it doesn't really make much of a difference. It's just good to know the alternatives because sometimes there are some hiccups with some of the packages, and it's good to have an alternative in case you come in run into a hiccup. Okay, so enhance, we're loading 4,809 observations over 18 variables. We have systolic blood pressure. Here is a summarization, so we're visualizing these. And Abigail and Lara, we met earlier this week, if I recall correctly, right? And there was a discussion which variables to describe, and so I can show a little bit of a for loop how you can actually do this description a little bit more efficient. Abigail, were you able to program this? Hi, Ashley, by the way,
I just stuck with doing them individually for this one.
Okay, sounds good. So let's look into this loop because this can all be analyzed and coded quite efficiently with loops. So this is the histogram. So we're seeing here nice histograms. We have talked about histograms, how to set the breaks. This is a box plot. I would not necessarily depict data as a box plot, but we can do that once we have several nominal categories of categories. Then we have the table. So this answer key only discusses the visual description of the response variables and the independent variables. So Tabor will essentially give us counts. So if we use the Tabor function and we're using the Tabor function on a dummy variable, on a binary variable like alias now, we essentially get counts for each of these categories. With the proportion table, we essentially get percentages or proportions for that matter. So if we do proportion table multiplied by 100, that actually should give us percentages. Yes. So hypothetically, you can you can alter them to show percentages. So R is very intuitive and we'll really do chunk by chunk by chunk. But let's keep the proportions. I think that's fine. Okay, so now what we want to do next, we basically want to do education levels. So we know the table function now. This here is actually superfluous. So the edu levels. So this is a little bit, that's a little bit of a catch, and I think Abigail, I think you dropped into that one, right? So what we're doing here is attributes gives you the actual entries. Another way to do that is to do enhance education. Will also, so these are the entries, and this gives you the values, the labels. So usually one way I would approach it with the way I'm doing factors, I would do it with the unique function, which here in this case gives you equally so the entries, and it gives you the actual labels. With the $ label, you actually get to the labels. So you find out what labels are contained in your variable. So if we are recoding edu levels into attributes, with the attributes, we essentially we're getting the attributes that are contained in the variable. So this gives us these, right? So we have here the different labels. Label 1, education, and we have here the different labels. We have not graduated from high school, which is a 1, graduated from high school, which is a 2, graduated from college, which is a 3. If we are assigning now edu levels to labels, we are getting the object edu levels that essentially is transferring these labels directly to edu labels. So you need that because you want to recode educations. And personally, I would always, I would not. Okay, now, okay, so what we're doing here is we're creating a new education variable. We are relabeling that, and we're building factors. We're building factors using the different levels of edu levels that we have quantified here from the attributes labels. So now the factor is always coded in the following way. So you basically you have education, which is your raw variable, right? This is 0, 1, and 1, 2, and 3, and NA. So then we have levels, and the levels we have from the labels file, and the labels per se come also from the edu levels because they are the associates then. So that's actually a very elegant way. You can also do that manually. You can say levels is 1, 2, 3, and you can say labels is that. So you can basically then you would replace the names with C. So this would look more like this, where you can do. So this is the manual way to do that. You can do education levels. Levels would be 1, 2, 3. And labels would be C, no, we do not graduated. And, that's how you would manually do it, right? But Marcel and Pino have here much more sophisticated approach, obviously. And so there's one thing you need to be careful because as soon as you do manually, the relabeling manually, you essentially run into a problem that then everything is case sensitive, everything is dependent. Like if you have here a little space and you copy the space into, R will have naked. So this would be this would essentially be the manual way of doing that. Is it necessary? No, it's definitely more elegant, but so running this will now recode our education variable into eduf. Putting this into table will give us, just like with mail, will give us the count. With proportion tables, we get the proportions. It's easy so far, right? It's not that complicated. Then we have the pairwise relationships. We want to see now, and there are several ways, and these are the same ways as Marcel and Bino have made in the lab file that we have discussed in class. So we have the tabli function. So the tabli function, I highly recommend to study those and get comfortable with those. So you can easily apply in R. So you find this ample tutorials on how to use the apply family here from DataCamp. And I think it's actually part of intermediate R, if I'm not wrong. So there's like apply, lapply, sapply. So there are various ways how to use apply, and it's quite a powerful tool. So I would highly recommend that you have a look at that. I personally do a lot with aggregate because I'm just peculiar about this. I personally prefer the aggregate function, and I would use that for my analysis. I would use the aggregate function. Okay, but essentially what you can do this in the same fashion with all three codes. Tabli will essentially require an X. The X is your response variable, whereas index is your actual factor. Then you give with FUN, you give the mean, and you give NA.RM equals true. NA.RM equals true is important because you have NAs. And we have seen those earlier. So if we do summary, enhance eduf, we see that we have 6 NAs here. And these can be manually removed, or these can be excluded from all analysis by essentially use the NR.RM function. It's usually the way I would handle it out in the field. I would not alter the original file. So once you download the file, I would always create a source file, and I would work from this source file. I load the source file in, and I leave that resting there somewhere in the environment. That's one file. It's a problem if it's like several gigabytes, then it's obviously a problem. But usually files are not as large. If they are that large, you will need to resort to different approaches anyways. But that's a whole different conversation, please. So now with a file in that size, you can leave one enhanced source file, and then you basically work with a little object. If you want to remove then the NAs, you can do so, and you take them out. So if we have now aggregate, if you would do NA.RM equals false, it should also give you essentially blood pressures for the NAs. No, it doesn't. Okay. Yeah. So that would need to be recoded then. So then you would need to recode the missings, and you would need to define. So if you set all NAs to something like 999 or something like nonsensically, you separate it from the overall factors, and you could include a factor that would allow you to calculate the blood pressures for the missing values. So this is something some journals would request that you say like, okay, so we have some missings. We want to see whether there was a selection bias by you including those missing values. Please also give us the blood pressure means for the missing values, just in order to make sure that there was no selection bias that was introduced by you excluding the missing entries. Okay, tabli, then we have aggregate a little slower, but we get the same values. Then we have sapply, and sapply essentially gives you the same story. You split BPSY ppx sy1 according to edu. You get the mean, and you get an nr.rm equals true. You can use every other function. Obviously, you can use SD. You get standard deviations. You can use median. Get to the medians. So there are several ways how you can approach this. It's as you can imagine, it's a powerful tool to essentially populate tables with it. Okay, any questions with that? I think it's fairly intuitive, right? If we continue now slowly.
Sorry, I have a question. So
Yes.
why did you do for the pairwise analysis? Can you scroll up a bit? So why did you do all of these? Oh, yeah, with the T apply and aggregate and supply. What does that do for the describing the pairwise relationship? Is it setting it up for an actual comparison, or?
Well, so when you have a pairwise relationship between a continuous variable and a nominal variable, commonly the way you would approach that is by using essentially a t-test would be one way to look at this association, or an ANOVA, right? So the ANOVA essentially is also something that you can do with a multivariable regression, which we're going to do later on. And the idea of that is to basically approach this in a univariate fashion, to just like summarize and visually kind of go on that first level of describing your variable and the association. So if you have a situation like that, where you have a continuous variable and you just want to see whether this continuous variable changes between the nominal levels of the categorical variable, the easiest and best way is always to show this as a box plot. So this is essentially what we're doing here then later on. And this is essentially how you will need to think of that. So you basically, you have a continuous variable that you're showing as per the respective entries for the nominal variable. And by that, you basically can visually compare whether there's a trend, for example. So if you, for example, if you stratify this as per tertiles of some other parameters, you would see trends. You could do like a visual trend analysis and then formally approach it using an ANOVA or using a multivariable regression.
Okay.
So this is kind of this first step, right? You kind of, the first thing you always have to do with all analysis, you need to get a feel for the data. And this is why this whole descriptive statistics business is so super important, because by summarizing your data, by looking at a summary, by mapping it out as an histogram, plotting it in that fashion as a box plot, as different categories, you get a feel, you get an idea, what is this data, what does this data look like? Like, for example, when I look at blood pressures, I see blood pressures in the realm of like 200 to 250, there's something off. There's something majorly off. And so 250 is like, I'm seeing in the dialysis population extremely high blood pressures. But the 250, I don't buy into it. So there is either there's then some form of a measurement error, or there's really something extremely paradoxical going on. Likely it's a measurement error or it's a transfer error. But again, you only can do this assessment when you actually have visually assessed it. And a box plot is just a good way to do that. A histogram is another way. And you would do this as the very first step, and you would then determine ranges of acceptable values. So if you have, you would always, for your analysis and for your data, for the data reading, you would kind of determine ranges that you're willing to accept in your analysis. And they are just values that just cannot be.
And could I just ask, with those, the very high values, those are all, you know, the outliers, the mean
Yes.
is actually
Yes,
much more centralized, which I guess just, I was surprised when with the regressions later on with the intercept, and like that seemed very low.
Yeah, so again, I based on that data I'm looking at here, I would think this is actually not really enhanced data, but it's more like a simulated data set. But again, that's me extrapolating here. So, but we have here a mean of 127. We have a median of 122. So the median we actually see here. So this is 122, and this is not graduated from high school. And we've graduated from high school, but not college. That's 120, and then we have 118 for those graduated from college. So these are the medians. So again, you would always do that, right? You would look into mean, median, standard deviations. These are the basic statistics you would be looking at. You look at the 25th, 75th percentile. You get a feel for it, right? If the mean and the median are different, you know, there's some skewing going on, which you may want to explore. If you look then at your actual box plot, you see that skewing, right? So the $1 million question: which direction is that skewed?
Left.
Well, so there was a 50-50 chance
sorry.
that you're right.
And I got the wrong 50. It's skewed towards the 250, right? Which I guess actually, if you're looking at,
Yes.
I flipped it this way, but it's skewed high, right?
Exactly. Yeah.
So then
exactly.
it's the
So
tail is actually to the right if you're.
The
So I got the
tail
wrong
tells the tail, exactly. So it's right skewed or positively skewed. Yes. So yeah. So this is essentially what you would be doing, right? So you describe the data, you get a feel for it. That's the idea behind it. And this is really this is the most important thing. Is like there's this often quoted line, garbage in, garbage out, right? It's like you're entering data, you're reading in data that doesn't make sense. Your output will not make sense. So this is really, I cannot emphasize how important it is. I can really not overemphasize it. So, but this is basically this first step. This is this univariable kind of depiction of whether there are differences. You can t-test it, you can compare it, or you can wait just for the multivariable regression and look at it there, which is essentially nothing else but an ANOVA. You would always, since it's more than two groups, you would prefer an ANOVA over the t-test for that reason. So what is the reason? Why are we doing an ANOVA over t-test? There's one really important reason for doing that. So you have, with every test you're doing, with every formal comparison, you're accepting a type 1 error, right? So when you run a t-test, your the acceptable type 1 error is the type 1 error rate is at 5%. So you're willing to accept 5% of an error that you see a difference, or you conclude the difference that is that you wrongly consider a difference between two groups significant, although it's actually not. And this is the 5% threshold. This is the type 1 error. That's your 5% p-value threshold. So your p-value, if your p-value is smaller than 5%, you consider this significantly different between not graduated from high school versus graduated from college, or versus graduated from high school but not college. So this type 1 error, if you do now 3 groups, if you do 2 groups, you have 5% of type 1 error rate. If you do 3 groups, this actually exponentiates to the power of 3. So you're suddenly looking at a type 1 error rate of 15%, because you have 5% for each comparison, you have 3 comparisons. And as a consequence of that, you're being asked to use an ANOVA, where the ANOVA, the null hypothesis of an ANOVA, and this is now recap from your introductory statistics, so I highly recommend you revisit that. So you are at this point hypothesizing, and that's the null hypothesis, that there's no difference of either group from the so-called grand mean. And the grand mean is the mean of all 3 groups. So that's the response variable over the entire population of all 3 groups. And your null hypothesis is that there's no difference. if the ANOVA is significantly different, and then we have the F statistic and the F distribution, and we have one tail, that's basically the cutoff. You remember that from introductory. So if the ANOVA is significant, that means that at least one group is significantly different from the grand mean. As soon as you have that, then you would go into pairwise testing. Then you test group 1 versus group 2, group 1 versus group 3 versus group 2. Then you do the 3 comparisons, because then you have a precedent, and you have a piece of evidence that there's a significant difference. So this being said, then you do another thing, because then you need to kind of adjust, and you need to take into account that you have multiple comparisons. So that's when you do the so-called Bonferroni correction, or you do a Taki honest significance testing, Taki HSD. So these are the ways how you would approach that practically. Or you use the ANOVA in the multiple regression. So now let's carry on. Any questions on that? It's just a quick recap. Okay. So we have now affected what is called EDU levels. These are our groups. We know that. We know the counts, we know the proportions, and now we want to regroup it. We want to create one group. We want to create one dummy variable, which is no high score. So no high score is basically, so we're testing whether education equals 1, and education equals 1 is no high school, no college, no high school, and no college. So we do yes equals no, no equals 0. Okay, so now we have this, and our no high school. So now we have no high school is now 0s and 1s. So if we're summing this up, we say sum enhance no high school. This is the NA that is plaguing us. So now again, we need to use the ni.rm equals true. So now if we have a table, enhance, so enhance AUFF, okay. So if we have the table here, we have no high school, 1,323. So now we do the other one. We do enhance high school. So these are the guys that did high school. So either this individual had 2 then it was this individual who had high school only. So now if we are recoding that, sorry, if we're recoding that, we essentially get now those individuals that do have high school only, and we're getting those that had either no high school or those that had high school and graduate school. So we are essentially now looking at, if we do this now, we're summing this up now. So this is now 2518. These are these guys now. So this is how you recode this in dummy variables. So now we can add in our model, we can code now no high school and high school as dummy variables. And we're getting now actual values. So this is now coding this into our model. So we're getting now estimates, which are essentially consistent with the difference from high school to college, or college, yeah, or no high school to college. So if we are recapping out this one, hold on. Look at the tabla. So we are coming now from high school, and this is probably what you should keep in mind for the homework as well. So essentially, when you have graduated from college, you have 120.7396. If you add to that 3.71346, you're getting now to the 123. If you're adding 5.002, you're getting now this is adjusted up. Okay. Okay, this is not working out like this, but yeah, so this is adjusted for gender, right? So we would need to, if we would do this calculation now, we would need to remove the age and the gender. So obviously this is affecting now the association. But yeah, hypothetically, this is how you can calculate it, and this is also how you can calculate it for each individual, which you will need for the homework and for the exam. Okay. But basically our fit one is here basically depicted with college students, college graduates as the reference group, and we have no high school and high school. If we are now moving forward, and we want to do this in a different way, we're going to do this by building factors. So we have done these factors already, so that should already be here. Then we have contrasts. Contrast essentially shows you exactly these dummy variables, right? So now the factor will now show in effect what reference groups do we have defined. So if we have not graduated and graduated, these are our zeros, and right now the reference group is graduated from high school. So we have now graduated from college, would then be a 1. So if we are now re-leveling that, we get now graduated from college as the actual reference group. So if we do the reference now, we essentially get now graduated from college as the reference group for both comparisons, right? Make sense? So this is for all analysis now our reference group. And now if we are running the same comparison, we essentially get the same factors here, and this is the same difference. So this is why this is important to understand the re-level function. And there was some discussion about Andrew. So I'm not sure who posted that discussion about Andrew. But yeah, so with re-level, you're defining that reference group, which essentially from which you're getting then your estimates as the difference from of your response variable.
Could we have kept our reference group as some high school or no high school degree?
You can readjust. You can make your reference group as you want. It does make a difference. It's
sorry.
Hmm?
I was going to say we wouldn't have to have used the re-level if we kept the reference group as high school.
Well, you needed to because it was asked for in the lab. So the reason, so when you think of it, put now your glasses on as a researcher and you want to do an analysis. Your research question will drive which one is your reference group, right? You got to think of it that way. If you are interested exclusively into graduate students and how they are comparing to the rest of the world, you will need to make your reference your reference graduates the reference group. And this is how you look at it. This is in this example. Well, this is a very peculiar example, but think of it in survival analysis, right? For example, it's the same conversation. It's the absolute same conversation and it's the exact same code. And you will do this in much detail in BIOS2 with Professor Wharton. And this is essentially with this knowledge that you're obtaining now on how to re-level things is very, very important. So these codes are really very central to what you will be learning later on. So really make sure you familiarize yourself with them. Okay, then what are we doing next? Yeah, so we just did that one, right? Same story, the factor for gender, and I think that's already it. Was there another lab question? I think that's it, right? Yeah, we did dummy variables. We used the fact function. So we changed reference category for the categorical variable, and this is lab 4. Any questions? It's straightforward, right? It's like it's just, I think it sometimes I think these sessions are kind of important. Like I just want to really keep pace with you and hear your concerns and what I can be of help with. So let me know if there are any questions.
Hi, Professor.
Efficient and yes. Hi, Uma. Yes.
Yes. Hi.
Hello.
Hi.
Yes.
I have a question. I'm having an issue installing Mictex to like the package to my R.
Okay.
To R, and it's for some reason it's saying that it's unrecognizable.
It's unrecognizable.
Abby was the one that showed me how. Yeah, it's a little. I don't know if it's. I don't know what the issue is. It's just saying that it's not there, but I did download everything for it. I have it on my computer. It's just not working for some reason.
All right. So I think this is. Let's conclude first the lab 4 session. So I'm not sure we should.
Sure.
Well, and yeah, let's do that first, and maybe we can do screen sharing then. Okay.
Sure,
any
sure.
questions concerning lab 4? If not, I think we're through this lab 4, and I actually am going to stop the recording. And thank you very much. I will
Thank you.
upload this, and I will put a YouTube link up.